a period DC circuit. Okay, the inductor act like the short circuit to the DC current. Yeah. Okay. Next one from the current dividers. Okay, from the current dividers technique. Okay, the current flow in here split into branch. Okay, you can determine IL from the current divisions technique. Okay, IL equal to all current flow. Okay, 10 milliamp. Okay, multiply with the resistance in another branch, 10 milliamp multiply with the 60 ohm. Okay, divide by the sum of them. Okay, sum of this equal to 60 plus 40, give you here. Okay, therefore the inductor current at time infinity equal to 6 milliamp. 6 milliamp. Next one, okay, determine the inductor current for time greater than 0. For this step, okay, you must determine the equivalent resistor and the equivalent inductor. Okay, from this circuit, you can see that you check at time. Okay, you can see that you can check at time greater than 0. For time greater than 0, the switch is already contact in this position, right? And you have one current source. You must kill the current source. How to kill the current source? You kill them by open circuit them. Okay, after you open circuit them, okay, you have two resistor contracts with the series in front of the inductor. Therefore, the equivalent resistor equal to 100 in this case, 100. That's why where it came from. Why the 60 must connect in the series with the 40, because from the circuit structure, after you kill the source, okay, the remaining inductor and the remaining resistor will be combined in the suitable form. Okay, now the time constant equal to, yeah, the time constant equal to here, okay, equal to 1 milli or, okay, 1 milli here. And after you dash, okay, after this, you substitute IL, okay, at time infinity equal to 6 amp, okay, 6 milliamp, okay, and here, 1000 for this case, time constant, okay, time constant equal to 1 milli or reverse them, it give you 1000. This is for the inductor current at time greater than 0. Now, okay, you must determine the initial condition I0. Okay, from the third characteristics of the inductor, it is impossible to change the current through an inductor IL by a finite amount in 0 time. Okay, IL is here 0 for time less than 0, and for time greater than 0, the inductor IL or the inductor current equal to 6. Subtract with I, e power 1 minus 1000 t. Okay, you can, from this situation, you substitute every t to be 0. Okay, and you can get that I equal to 6 milliamp. Substitute them in there. Okay, you can get the general form of the inductor current to be 6 minus 6e minus 10,000 minus 1000 t. Okay, after that, okay, after here. Next, okay, after that, the questions ask you for the inductor's voltage. Okay, we have for time less than 0 because, okay, no current flow in the inductors, okay, no voltage across them, okay, therefore the inductor current equal to 0 and the inductor's voltage equal to 0 too. Okay, for time greater than 0, okay, the inductor current equal to 6 minus 6e minus 1000 t. Okay, take derivative of them. Derivative of the first term is constant. Take derivative of the second term. Take derivative of the EAT, give you EAT. A in this case equal to 1000 minus 1000. Okay, you get the inductor's voltage is here 0.6 E minus 1000 T. Next one determines the other parameters such as the resistor's current. Okay, the current flow in the 60 ohm. Okay, here for time less than 0, check from the circuit. For time less than 0, you can see that, okay, for time less than 0, the source will be bypassed or the short circuit by this switch. Therefore, no current flow. IR is a 0 ohm. Okay, but for time greater than 0, derive IR in the term of the inductor's voltage. Okay, express them. Okay, when the switch is open, okay, you know the current flow in here, okay, 10 milliamp, and the current flow in this branch equal to IL. 3 current, okay, Yeah, therefore the I6 ohm equal to 10 milliamps subtract with the inductor current. Okay, give you here to write that. You can see that if the questions ask you for the other unknown parameter, derive them from the inductor current. Okay, therefore I6 ohm equal to 4 plus 6 E minus 1000 T milliamp. Okay, if the questions ask you for time equal to 1.5 seconds, give you here. Okay, the inductors. Okay. Now for time less than 0, the inductor's current is a 0 because it has no source feed to the circuit. For time infinity, the inductor's current will be reached to 6 milliamps soon. Okay, and for time greater than 0, okay, the inductor current will be increased in the exponential form. Okay, reach to that point. 1.1 and 1.3 is equal when time equal to 0. Okay, you can find I in this case as the okay. Next step, you determine the inductor's voltage. The inductor voltage to derive them from the inductor current. For time greater than 0, okay, it equal to 0. For time greater than 0, you take the derivative of the inductor current L di dt. Okay, the shape of them is here. Okay, therefore the inductor's voltage will be jumped to be 0.6 volt immediately, and after that it will be dropped to 0 soon. Okay, for the resistor current, for time less than 0 is 0. Okay, because it have no source feed to the circuit yet. For time greater than 0, okay, the current flow in the 6 ohm is came from the source, okay, and came from the inductor current, okay, equal to, but it must be dropped to be 4 milliamps soon. Okay. I will provide you this exercise. Okay, I think if you do by yourself, you will know. Okay, you understand them a little bit one. Okay, now we go to the next part. Okay. Okay, can you see my slide?
Yes.
Okay, the chapter 9, okay. The next chapter is, okay, that will be formulated from the previous 2 chapters, okay. Which came from the idea of the chapter 7 and the chapter 8. The chapter 9 discuss about the circuit that contain all the resistor, inductor, and capacitor. Okay. This section is present of the inductance and the capacitance in the same circuit. Will produce the second order system, or you can classify them to be one linear differential equation that include the second order derivative, or two equation, two simultaneous linear first order differential equation instead. The RLC circuits does not only appear very often in the practical, but also do very well as the model for the other type of the system. The RLC circuit can be used to model the suspension of the system of the automobile too. Okay. The idea of the RLC circuit will be separate them into two main groups. The first one is the RLC in the parallel. Okay, after the switch is activated, okay, the structure of the R, L, and C will be connected in the parallel structure. And the second one is, okay, after the switch is activated, okay, the RLC will be connected in the series instead. Okay, therefore we classify them to be the parallel and the series. Okay, and after that we consider is about the driving short case. Okay, now we consider for the short free first. Okay, the short free parallel circuit. Our first task is the determination of the natural response, which again is the most conveniently done by considering the short-free circuit. We may then include the DC short, switch, or the step short into the circuit, representing the total response once again as the sum of the natural response and the forced response. The understanding of the natural behavior of the parallel RLC circuit is fundamentally important to the future study of the communications network, the filter designing, as well as many other applications. The first idea is about, okay, the differential equation of the RLC's parallelly. Okay, you can see that the structure in this figure is, okay, after the switch is activated and if it have no short, after you simplify that, okay, the resistance that you have will be connected in the parallel with the inductance and the capacitance. Okay, the top of this node, okay, you can apply the Kirchhoff current law, okay, and you can express that IR plus IL plus IC equal to 0. Okay. Now with the reference of these circuits, we may be write the single node equation here. And after that, you express every I in the term of V. Okay, in the term of V. IR, V equal to IR, I equal to V divided by R. Okay. For IL, okay, equal to 1 by L integrates V dt. Okay, and the initial condition. And the last one, okay, IC equal to C dV dt is here. Okay. After you get this equation in the equation, okay, you formulate you can model the circuit by the equations 9.1. Note that the plus sign is a consequence of the assumed the direction of the inductor current. And we must solve the equations 1, okay, subject to this initial condition. Okay, IL at time equal to 0 equal to I naught, and VC at time 0 equal to V naught. Okay, with the both sides of the equation 1 at differentiates 1 with respect to time. Okay, you differentiate all equation again. Okay, the result is the linear second order homogeneous differential equation show you in equation number 4. Okay, the unknown, you can see that the unknown of this, okay, the unknown of this differential equation in the term of V, in the term of V. V is mean VC, the voltage across capacitance or the capacitance voltage, okay, whose the solutions VT is the desired natural response. Now, this equation, with the next step, we will apply the EMS skill to solve them, okay, but I will briefly discuss about that, okay. Thus, the auxiliary equation of the characteristic equation is here. You differentiate 2 times, give you S squared, okay. Differentiate them 1 time, give you S power 1. No differentiate them, give you S power 0, okay. You get this characteristic equation and you can determine S from the quadratic equation. Do you remember the quadratic equation? AX squared plus BX plus C. X equal to minus B plus minus square root B squared minus 4AC divided by 2A. Okay. Since the equation number 6 is the quadratic equation, there are 2 solutions that you solve from this previous equation is here. You get S1 in the equation 7 and you get S2 in the equation 8. We thus have the general form of the natural response is here. From the first order, you get only one S, okay? S will be in the term of EST, but in this case, you have 2 S, S1, S2. The form is the same, A1 ES1T plus A2 ES2T. Anything? Hello? Michael, Adisak, I heard your voice. Anything?
Yeah, I'm so sorry. I'm so sorry.
Okay. Okay, I think you have something not understand. Okay, if I go too fast, okay, it's lecture so fast. Okay, you can tell me. Okay, now the next step. Okay, from the auxiliary equation, you get here and you get here. Now we just have the general forms of the natural response. Where S1 and S2, okay, is given by equation 7 and 8. Okay. A1 and A2 are the 2 arbitrary constants which are to be selected to satisfy these 2 specific initial conditions too. Okay, you can see that you have 4 parameters. You must determine S1, S2, A1, A2. S1 and S2 you determine from RLC value directly from the equation 7 and 8. But as A1 and A2 you must use the initial condition. This initial condition that you use is here. Okay. Okay. IL 0 minus. Okay. IL at time 0 and VC at time 0 we call I naught and V naught. Okay. VO. Okay. Next one. Okay. The constant S1 and S2 in this case, it can be real or it can be complex number. It's different from the first order case. The first order is, okay, S that you solve from the first order's equation must be real only. But in this case, it's from the quadratic solving, it can be real or it can be complex, okay? The constant S1 and S2 can be real or complex conjugate number depending upon the value of R, L, and C in the given network. Let us define the new term, omega 0 and the resonant frequencies, okay? Omega 0 is here, equal to 1 divided by square root LC in the equation 10. And we define, let us define and another term, alpha, or sometimes we call them the nimble frequency or the exponential damping frequencies. The measure of how rapidly the natural response decaying and the damp out to its steady state final value. Okay, alpha equal to 1 divided by 2 RC. Okay, after this, okay, you can see that you can substitute alpha and omega in the S1 equation. You can see that the form of the S1 equation is seem easier. Okay, S1 equal to minus alpha plus square root alpha square minus omega square in the equations 12, and S2 is the same. Okay, you substitute them. S2 equal to minus alpha minus square root alpha square minus omega square. Therefore, after this, you must remember alpha, omega, and remember S in the form of alpha, omega. Instead, you remember them in the original form. Okay, remember equation 10, 11, 12, and 13 respectively. Now, why I order you to remember this? Because in the near future, we will use this to solve them. The natural response of the parallel RLC circuit will be expressed in here. Okay, the general solution is in equation 9. Omega, express them in the equation 10. Alpha will be expressed them in equations 11. S1 and S2 will be in the form of the alpha, and the omega can be expressed in the equations 12 and 13. We know two basic scenarios possible with the equations 12 and 13 depending on the relative size of the alpha and the omega, dictated by the value of the R, L, and C. We have three cases for this solution. The first case is if the alpha is greater than omega, therefore this term will be positive. If this term is positive, it means the square root is real. You get 2 S1 and S2, okay, is both the real number for this case, okay. This case we call them the overdamped case. The second case, in the case that if the alpha is less than omega, this square root term will be negative and it becomes the imaginary number. Therefore, it makes S1 and S2 to be the complex number instead. And the last case, if the alpha is equal to the omega, this term is the 0. It means S1 and S2 is equal and it equal to minus omega. Okay, for this case, alpha equal to omega 0. Okay, therefore, S1 and S2 will be both the same real number. Now we consider for the first case, the overdamped case. Okay, a comparison of the equations 10 and 11 show that the alpha will be greater than omega. Okay, if the alpha is greater than omega, okay, alpha equal to 1 divided by 2 RC, omega equal to 1 divided by square root LC. Okay, it's greater than, you recognize it. Okay, and S1 will be 1, okay, the real number. S2 will be another real number. Okay, both of them is, okay, S1 and S2 is negative real number. Okay, since the absolute value of S2 is larger than that of S1, then the terms containing S2 have the more rapid rate of decrease. We may the general form of the natural response show you in the equation 9 here. Okay, the general form. V equal to A1 ES1T plus A2 ES2T. In order to give you more understand about the overdamped case, I will provide you the example first. Okay. For the circuit of the following figures, determine the voltage label V, okay, when we assume the two initial conditions to you, V0 equal to 0, IL0 equal to 10. Okay, V is mean VC. Okay, in fact, even though it's VR, VL, and VC is equally, okay, but we frequently refer them to be VC. Okay, determines the capacitor voltage first. Okay, now alpha equal to 1 divided by 2 RC, and R, the resistor, equal to R equal to 6. Okay, C equal to 1 by 42. Therefore, alpha equal to 3.5. Next one is omega 0. Omega 0 equal to 1 divided by LC. The L equal to 7 Henry. C equal to 1 divided by 42. Therefore, omega equal to square root 6. Square root 6 is approximate to be 2.6 and 2.7. Therefore, in this case, this alpha is greater than omega. Okay, if the alpha is greater than omega, okay, S1 and S2 is a real number. Therefore, in this case, it is the overdamped case. S1 equal to -1. Okay, and S2 equal to -6. Okay, you substitute S1 and S2 in the general form solution of this V. Therefore, you get the capacitor voltage equal to A1 E minus T plus A2 E minus 6T. Next step, you must determine A1 and A2 by these two initial conditions that the questions are for. Okay, provided to you. At time 0, Vt equal to 0 too. Okay, Vt equal to 0. Therefore, substitute every T to be 0. 0 here. Anything power 0 give you 1. Okay, anything power 0 give you 1. Therefore, 0 equal to A1 plus A2. But in this case, this will have the one equation, 2 unknown. You cannot solve it yet. You must substitute the second initial condition first. And the second initial condition, okay, we apply the KCL to the top of this node, okay? You express every current in the form of the voltage across them, except the inductor current. Because the inductor current, you already know that the inductor current equal to 10 amp. 10 amps, okay? For the resistor, IR equal to V divided by R, okay? For the capacitor, current, IC equal to C dV dt. You know that, okay, V VC equal to A1 E minus T, A2 E minus 6T, okay? You take the derivative of them, okay? Substitute them is here. Okay, after you substitute that, okay, is, okay, V at time 0, in the previous give you 0, right? In the previous initial condition. Okay, IL for time 0, it equal to 10. Equal to 10. Okay. Okay. V at time 0, okay, equal to 0. Okay. Now you take the derivative of this term, give you here. Take the derivative of E minus T, give you minus E minus T. Take the derivative of E minus 6T, give you minus 6 E minus 6T. Okay. And you substitute every T to be 0. Okay. Anything power 0 give you 1. Okay. Therefore, in the final solution, you get minus A1 plus minus A1 minus 6A2 equal to 420. Okay. And from this equation, okay, equation number 15, equation number 16, two equation, 2 unknown, you can solve that, okay, A1 equal to 84 and A2 equal to minus 84. Okay. Now in the overall point of view, what happened? Okay. You can see that the inductors, the capacitor voltage equal to 84 E minus T minus 84 E minus 60. Okay, it's here, minus C. Next one, the first term is represented by the blue cloud. The second term is here, the green one, okay? And yeah, it's have minus in front of them, okay? It reverses the cloud to the bottoms, okay? Reflected in the horizontal axis, okay? You add between A1 and A2, it provides you here the red one, You can see that the red one, the result of the red one, due to the blue cloud always higher than the green one. Therefore, the red cloud will be the result of the subtraction. It always positive. And if the result is always positive, it means the result is all over the axis. We call them the overdamped in this case. We may interpret the first exponential term as having a time constant of 1 second, and the other exponential is a time constant equal to 1 by 6 seconds instead. It starts with the unity amplitudes, but the later decaying more rapidly. The response curve of the 0 at time equal to 0, okay, you can see that it equals to 0, okay, and the 0 at time infinity again, Okay, at time infinity, the response will be 0 again. Okay. But the graph will be never negative since there is nowhere, not everywhere is 0. Okay. The second case is called the critical damp. Okay. The critical damp is the special case. Okay. When omega is exactly equal to alpha, is exactly equal. Okay. In this case, in the real situation, the critical damp is very, very extreme exists in the nature's network because you know that the resistance value, the capacitance value, and the inductance value must have perfectly matched in this equation. But in the real situations, the resistance, capacitance, and the inductance always have some error. Okay, maybe 5% or maybe 10%, depend on the chip that you implement them. Therefore, if it has the error, this equation is not never matched in this form yet. Okay. Now for the critical damp, alpha equal to omega, therefore S1 equal to S2. S1 and S2 are the same negative real number. And if we were attempt to construct a parallel RLC circuit that is critical damp, we would attempting an essentially impossible task. For we could never make alpha exactly equal to the omegas in the real world. Now, but for the theoretical, it's possible. Okay, the differential equation will be expressed in here. Simplify them into the equation 4, and we made general form of the natural response here. Okay, V equal to E minus alpha t, A1 t plus A2. Okay, alpha, you know that equal to here. Okay, now the next step will be provide you the real the example case. For the circuit of the following figure, determines the voltage label V. Okay, V, yeah. Determine the voltage across this terminal. Okay. Now for this general form is here. You know R, you know L, you know C. You can determine alpha. Okay, alpha equal to square root 6 or 2.6 or 2.7 approximately. Omega sub 0 equal to 1 divided by square root LC equal to 6 again. You can see that both of them is identical, right? Alpha is exactly equal to the omega. Okay, it becomes the critical damp case. Okay, you substitute them, you get S1 equal to minus 6 and S2 equal to minus 6.2. Okay, substitute them in here. Okay, square root 6 is here. Okay, now you must determine A1 and A2 for this step. And the A1 and A2, you can determine them from the initial conditions. V at time 0 equal to 0. Okay, substitute everything to be 0. Anything power 0, give you 0. The T by 0. A1 multiply 0, give you 0. Therefore, you can determine A2 from this equation. And in this equations, A2 equal to 0.2. Okay, next step, you determine the inductor current at time equal to 0. Yeah, okay. Substitute them. You express them, okay? Express them, apply the KCL to the top of this node and express them in the term of the voltage, capacitor voltage, okay? And substitute them in here, okay? Except the inductor current that you know that, okay? The inductor current equal to 10 amp, okay? Express them, okay? You differentiate the first term is here, okay? Differentiate E minus square root 6t equal to square root 6. Okay, and substitute them. You get A1 equal to 420. Okay, 420. Now, after A2 equal to 0, when you substitute them, the general form solution will be equal to Vt equal to 420 t e power minus square root 6t. Okay. Okay. Now, the next step, okay, we will try to plot what about the response of this graph. The response of this graph is comprised by t and by the exponential term, okay. You can see that at time 0, t equal to 0, everything 0, okay. And when time increasing, okay, the exponential e minus square root 6t will be increase the effects or the impact in your solution. Therefore, the solution will be decreased from time to time. The key that we call them the critical dampings mean this point is very, very critical in your system. Okay, if it tune them more lesson. Okay, it will classify to be the overdamped. The overdamped is mean the peak of them. Okay, even though it have no oscillate, but the peak of them never reached the critical damp yet. Okay, the critical damp is you can see that the overshoot or the maximum of the critical damp case for this case is about the 63 volt. It's larger than that obtained in the overdamped case that only about 49 volt instead. The selection of the value R will provide the critical damp which always give a shorter settings time than any choice of R that produce the overdamped case. The last one is for the underdamped case. A comparisons of the equations 10 and 11 show that alpha will be greater than omega. Therefore, you can summarize that for R squared C squared is greater than LC. Okay, and you can determine the S1 and S2 in this case. S1 and S2 is a complex number, and we now then the new radicals which is the real for the underdamped case and called is omega D or the natural frequency, the natural resonant frequency. Omega D is a reverse process. Omega D equal to square root omega naught square minus alpha square. Okay, the general form of the natural response may be rewritten in this equation. You grouping them, you can split S. S is the real part and the imaginary part. Okay, the imaginary part you group together, you can convert them into sine and cos forms. Yeah. Okay, in order to give you more understand, okay. Okay, for the circuit of the following figure, determine the voltage label V. If we assume that V equal to 0, V0 equal to 0, and IL0 equal to 10 amp again. Okay, for this case, okay, determine alpha first. Okay, alpha equal to 2, omega equal to square root 6 or equal to 2.7 or 2.8. Therefore, in this case, alpha is less than omega. If the alpha is less than omega, you must determine omega D instead. Okay, omega D is the reverse the term in the bracket. Give you omega square minus alpha square and give you square root 2. Okay. Now the general solution form in this case, we write them in the decaying exponential and sine and cos term. Okay, Vt equal to E minus alpha t multiplied with B1 cos omega dt plus B2 sine omega dt. The value, okay, determines the value of B1 and B2 from this circuit. Okay, you know that, okay, the first initial conditions V at time 0 equal to 0. Okay, at time 0 equal to 0. Okay, time t, every t substitutes by the 0. Sine 0 give you 0, but the cos 0 give you 1. Therefore, you have the B1 equal to 0 in this case. The second case is, okay, determines B2. Okay, determine B2 is, okay, the solution is here. V, the capacitor voltage is equal to B2 E minus 2t sine square root 2t. Okay, next one is the inductor current equal to 10 amp. Okay, at the top of this node, okay, you can express the current. Okay, 2 current get in plus, okay, and 1 current get out is minus in here. Okay, express them in the term of the voltage. Okay, in the term of the capacitor voltage. Okay, except IL, because IL, you know that IL or the inductor current will be 10 amp soon. Okay, 10 amp soon. Okay, so 10 derivative of EAT sine t is a little bit complicated because you require the chain rule skill. Okay, is, okay, differentiate f and g equal to f differentiate g plus g differentiate f. Okay, Vt for time greater than 0 is equal to 0, and this term sine 0 give you 0, 2. Okay, you get here. Okay. And you can get B2 equal to 210 square root 2. Okay. 210 square root 2 e minus 2t sine square root 2t. Okay, the solution, the general solution of this case is shown you in this figure. Okay, you can see that the overdamped case is lowered overshoot. The critical damp is mean it have the peak of the overshoot is okay, except you make the graph oscillate. Both of them, the red and the green, is the graph is smoothing decreasing. Okay, but for the critical damp is okay. Sorry, the red one is underdamped. The underdamped, some part of this graph will be negative. Okay, the critical damp is the peak that make the system will be get the highest overshoot before oscillate. The maximum of the underdamped case is about 42 volt is larger than the obtained in the critical damp. Okay, the critical damp is about 63.1. Okay, and the overdamped case is about 48.9 instead. When the damping is changed by increasing the size of the parallel resistor, the maximum magnitude of the response is greater and amount of the damping is smaller. The response becomes oscillatory when the underdamping is present and the minimum settling time is obtained by the slightly underdamped case. Okay, I will provide you this example. Okay, determines the capacitor voltage. Okay, checking first. For time less than 0, the switch is open and the source will be dry the circuit. Okay, and it make this circuit to be full charge. The capacitance alpha value equal to 1 divided by 2 RC. Okay, if you short circuit them, you can see that this the bottom section and the top section is separated. Okay, now alpha equal to 1 divided by 2 RC. Okay, alpha equal to 125k. Omega equal to omega naught equal to 1 divided by square root LC. You know L equal to 5 millis. And C, the capacitor equal to 20 nano. Therefore, for the omega equal to 100,000. 100,000. You can see that in this case, is alpha is greater than omega. If the alpha is greater than omega, it means it's overdamped case. You can determine S1, you can determine S2, and you can express them in the general form. In this case, you cannot find A1 and A2 yet until you use the initial condition. The first initial conditions, VL at time 0 and VC at time 0. We assume any transient in the circuits died out long ago, revealing the purely DC circuit, and the inductor act like the short circuit to the DC current, and the capacitor act like the open circuit to the DC current too. Therefore, is here. The inductor current equal to V equal to I equal to V divided by sum of R, and the direction will be reverse. The direction is reverse. Therefore, I minus 150 source divided by 20 plus 200 plus 300. You get the inductor current equal to minus 30 milliamp. For time greater for time greater than 0, the questions argue another one question is argue the voltage divider to determine VC. VC for time less than 0 is the same. You know the current flow into them. You can find the voltage across them. VC equal to 200 multiply with with the 200 multiply with 150. The voltage across them divided by the sum of them 200 and 300. You get VC equal to 60 volt. After that, you would like to determine A1 and A2 by the initial condition. And the initial condition in this case, V at time 0 equal to 60 volt. V at time 0 equal to 60 volt. 0 multiply anything give you 0. Anything power 0 give you 1. The same. You can get the first equation. A1 plus A2 equal to 60. Next equation, At time equal to 0, you must, okay, you know that the inductor current equal to minus 0.5 amp, 0.3 amp, okay. Therefore, the sum of at the top of this node, okay, you can apply KCL, IR plus IL plus IC equal to 0, okay, and you express them in the term of V, okay. But the IL, you not necessary to express them because you know that IL equal to minus 0.3 amp, okay. For VC, you substitute VC in here, okay. For VC times, okay, equal to 0, it equal to 0, okay. Reorganize the equation, okay, you can get here. Okay. You get A1 plus 4A2 equal to 0, okay. You get two equations to unknown, you can derive that, okay. A1 equal to 80, A2 equal to 200. Okay. In the overall polynomial, what happened? Okay, for time less than 0, okay, for time less than 0, the source is still driving the circuit for a long time. Therefore, the capacitor is performed like short circuit, and the inductor performed like short circuit, the capacitor performed like open circuit. Okay, for time less than 0, VC is 0. For time greater than 0, okay, for time greater than 0, VC is comprised by the two exponential term. Okay, this term, XD, E minus 5,000 T will be drop more rapidly than, okay, the first term will drop far slower than the second term. It provides you here. Ah, wait a minute. Wait a minute. Ah, okay. Can you hear me? Hello?
Yes, Ajahn.
Ah, okay. Capture this question, okay? Let's do it. Try to do it, and I will provide you complete solution soon, okay? Okay, stop sharing in 5, 4, 3, 2, 1. Let's do it. Okay. Okay, for attendance checking, okay, turn on the camera now. À, ว่าไงธนพัฒน์ลองโจทย์เสร็จยัง Hello? Anyone finish yet? If you finish, I will provide your solution. No one finished yet? Okay, we give you another 5 minutes and I will provide your solution, complete solution, okay, to checking the thing that you do is right or wrong and provide you another one assignment, okay. Remember that, okay. This is only 1 or 2 questions that you take the exercise in the real case. In order to make you full understand, you must take a lot, okay. Maybe 10 or 20 at more, at least, okay. Oh, no one finished yet? Hello? Can you hear me?
Yes, teacher.
Okay, I will provide your solution, okay? If you do by yourself, it's good, but if you don't, okay, I cannot help you, okay? In the real final, it's more difficult than this, okay? Okay, the solution of this is, okay, this question asks you about this circuit, okay? It determines the capacitance voltage first, because this circuit, oh, sorry, it's not IL, sorry, IL, it's not capacitance, okay? Wait a minute, it should be I. So capacitance voltage, sorry. Okay, yeah, okay. Okay, this circuit will be provide you the circuit contain R, L, and C circuit, okay, for the sort free, okay. Therefore, the key parameter for the parallel case, okay, for the parallel R, L, and C will be contract in the parallel. For time greater than 0 after the switch is activated, okay, for the X, all will be bypass short circuit. You have only 3 elements left, okay, this capacitor, this inductor, and this, okay, resistor, okay. Now, the first step, you must determine which case of them first, okay? Okay, overdamp, underdamp, or the critical damp. Okay, you know that it's already the parallel case. You would like to determine the capacitance voltage. Alpha equal to 1 divided by 2 RC, okay? R equal to 24 ohms, okay? C equal to 1 by 240, okay? Alpha equal to 5. Omega equal to, okay, 1 divided by square root LC. Inductors L equal to 10, okay, C equal to 1 divided by 240. Omega naught, okay, omega 0 sub 0 equal to 4.9. In this case, alpha is greater than omega. Therefore, you substitute them in the S1 and you can guess S1 equal to minus 4, S2 equal to, okay, minus 6, okay. This case is the overdamped case. You get difference value of S1 and S2, okay. The general form of the capacitance voltage will be here, A1E S1T plus A2E S2T, okay. Therefore, you substitute S1 and S2 in here, you get VC equal to A1 E minus 4T, okay, plus A2 E minus 6T, okay. Next one, okay, next one, okay, you must determine A1 and A2. But in this case, the way to determine A1 and A2, you must, okay, consider the case that before switch is activated. Before the switch is activated, it means the switch is open yet, okay, and the sort is, okay, is driving the circuit for a long time. U minus T is mean for time less than 0, the sort is activated. For time greater than 0, the sort is turned off, okay. Now for time less than 0, it equal to 3 amps constantly, okay. And in this circuit, we assume in the transient in the circuit style out long ago, leaving a period DC circuit, and the inductor act like the short circuit to the DC current, and the capacitor act like the, okay, capacitor act like the open circuit to that, okay. Okay, now you have there, okay, one current force split in two, okay. The key parameter that you would like to determine is here, okay, IL. Okay, the questions ask you about the four parameter, okay, IL and the VC, okay. You must get IL and the VC to use as the initial condition. The inductance current, okay, I flow in this, okay, equal to 3 amp, okay, multiply with the resistance in another branch by applying the current divider techniques, okay. IL equal to 3 multiplied by 24, divided by the sum of our resistance equal to 24 plus 48. The inductance current equal to here. And the next one, okay, the next one is here, the okay, we determine the capacitance voltage, okay, determine the capacitance voltage. Two resistor is connect in the parallel, you combine them and you can get all current flow is 3 amp, okay, you know the voltage across that equal to 40x volt in this case. You already get two necessary initial conditions, okay. Now we determine IR and the other because the questions ask for that, okay. IR for this case, okay, you can determine them from the current divider technique too. IR equal to 3 amp multiplied with 40x, the resistance in another branch, 40x, okay, divided by the sum of them. In this case, IR equal to 2 amp, okay? And I see for time greater than 0, the capacitor is performed like open circuit for full charge. You get IC, the capacitance current equal to 0. Now, we get, but we use only two initial value, okay? VC and IL. For VC at time 0 equal to 40x volt, okay? You substitute them in here, VC, and every T substitute to be 0. Okay, anything power 0 give you 1. You get, okay, the first equation A1 plus A2 equal to 40x. Okay, the second equation, okay, the second initial condition you apply at the KCL law. Okay, IL at time 0 equal to 1 amp. Okay, IR plus IL plus IC equal to 0. You express IR in the term of V and IC in the term of V2. Okay, IR equal to VC divided by R. Okay, and IC equal to C dV by dt. For IL, you know that IL equal to 1 amp. Okay, in here. You take derivative up here, C dV by dt, you get here. Okay, minus 4 A1 E minus 4T. Minus 6 A2 E minus 6T. Okay. And we see for the initial condition equal to 40x. Okay. Substitute them. Okay, you get the second equation here. Simplify this equation, you get 4A1 plus 6A2 equal to 720. Now you get equation 1 and equation 2. You substitute them, you get the initial condition. You get A1 equal to minus 216 and A2 equal to 264. Therefore, the general form of the solution is, okay, the capacitance voltage equal to minus 216 E minus 40 plus 200. Okay, 64 E minus 60. Okay, at time equal to 0.2, substitute 0.2 second in here, you get the capacitance voltage equal to minus 17.5 volt. For the other parameters, okay, IC for time greater than 0, you already get from the previous IC equal to 0. For time greater than 0, IC, okay, equal to C dV dt. Okay, equal to C dV dt. Give you here. Okay. And for IR, for time greater than 0, equal to 2 amp. Time greater than 0, derive them in the term of VC. Okay, you due to the, okay, the voltage across all equal to VC, the capacitance voltage. Therefore, IR equal to VC divided by R. VC you get from the first step. Okay, now R equal to 24, you get IR in here. Now in the overall point of view, okay, now IL. Okay. If the questions ask you for IL, derive them from the VCs, okay? How to derive them from the VC in this case, okay? IL is here, okay? In the term of IC and IR, okay? You know IC, you know IR in the previous step, okay? IC, okay? IR, you get from the previous step that you derive from, you derive them from VC. You get IL is here, okay? Now in the overall point of view for time greater than 0, okay? Okay, the capacitor is equal to VC, capacitance value voltage equal to 40x volt. Okay, capacitor perform like open circuit. Therefore, IC equal to 0 2. Okay, IR equal to 2 amp. Okay, and IL equal to 1 amp. Okay, 3 amp split in here, 1 flow in here, 2 amp flow in here. Now for time greater than 0, for time greater than 0, the voltage and the current will be dropped soon. Okay, the switch is pressed in this position. Okay, time greater than 0, the switch is present here, and 48 volt will be short circuit. Okay, 40x ohm, sorry, 40x ohm will be short circuit, and the source is gone from the circuit. Okay, yeah, it's only 3 elements left. Okay, VC will be dropped to 0 soon, but the shape of the dropping will be show you in here, and okay, IC will be show you in here, IR will be dropped to 0 soon, and here. Okay, you can see that's why IR will be 0 soon. Okay, in the circuit point of view, what happened? Okay, you know that the voltage, okay, and the current will be dropped to 0 soon every point. Okay, due to it have no source in the circuit. Okay, and in this case, the detail of each parameter and the detail for each graph will be show you clearly. Okay, I will show you every detail. Any question? Okay, Therefore, okay, okay, capture this question, okay. Can you see this? Capture this question. Can you hear me? Capture this and try to do by yourself, okay? Because I understand your situation. If you try to pick one of the question in the book to do it and it have no solution, you're not sure that the thing that you do is right or wrong, okay? Now, I give it to you, okay? If you want to do it, okay? If you do them completely, okay? Don't worry about not to submit it to me, okay? Next time, I will provide you the complete solution and you can check that the thing that you do is right or wrong, which part you right, which part you wrong, okay? Okay, clear? Stop sharing in 5 minutes, 4, 3, 2, 1, okay? Okay, good luck, okay? See you next time. If you don't have any, okay, question, okay, dismiss.
Thank you, Arjun.
You're welcome. ไม่รู้เดี๋ยวถามแม่ฮะ